Nice to see everybody, a lot of friends. So today I would like to talk a little bit about the method we apply. I can be very briefly on that because Jeff given already this morning a very clear introduction on that, and we more or less use the same method. So I can be very short on that. And after this introduction, I would like to discuss with you 3 applications, and I hope they are interesting for you as they were for me. Okay, our approach at the Institute is that we use the bioassay for all our monitoring programs. We use the bioassay CARDEX as well as the high-resolution mass spectrometry. We don't use the bioassay as a quantitative approach. We use it as you might call it a semi-quantitative approach. We use it mainly for the selection of the negative samples from the what we call suspected samples, not positive, but suspected samples. And the suspected samples have to be confirmed using high-resolution mass spectrometry. But as technology is moving on, we are discussing within the EU NRL network the use of other, let's say, alternative MSMS technology. And Martin already gave this morning a short presentation about MSMS. And I think it's very promising, and hopefully in mid-May we will finalize a draft proposal to the European Commission about the uses for the MSMS technology, not for screening only, but also for confirmation. The latest result I have been working, or the latest result I've seen, and I did it together with Rainer Madis from the URL as well as with Alexander Kotz from Freiburg. We worked on the MSMS technology using not electron impact ionization, but atmospheric pressure ionization. And by doing that, you gain a lot of sensitivity. And with this technology, we achieve the same sensitivity, more or less, as with the high-resolution MS. And we will continue to work on that technology together with the colleagues in Freiburg. So our method so far is first screening with the calyx and then confirmation, not only for the suspected one, but also for a small amount of the negative ones with a high-resolution mass spectrometer. The high-resolution mass spectrometer, we every year since last year. Oh, sorry.
I was wondering.
I think it's working really nicely. But
wait a minute. No, can you maybe use the keyboard if it's ready?
Oh, I don't know.
Does it work?
Oh, no, it works. Thanks. Okay. But now it doesn't work over here. Okay, doesn't matter. So this is our setup, screening using the CARDEX and confirmation of all the suspected, but a small part of the negative samples with the high-resolution mass spectrometer. Okay, when we look at the, let's see, where do we have? Okay, this is our high-resolution mass spectrometer, and the main advantage, and I will explain a little bit in detail how we operate this method. One of the big advantages of the high-resolution mass spectrometer, but also with the MSMS technology, that you get a quantitative result and you get a congener pattern. And congener patterns, like this example for instance, you can compare it with congener patterns you have been seeing before. So, and when you compare them, these are all kinds of patterns from different crises we have been working on in the past. So this was a new one, was one in 2004, and when you compare the congener pattern with the previous met ones, then you can make a conclusion sometimes, if you're lucky, this is the source or that is the source. Nowadays we are working on the German problems they have nowadays with the eggs again, and we just received the samples, and we hope by using these patterns that we can help these people with telling them this is the source, because if you don't know the source you can't solve the problem. Okay. This is our method. So you start with a sample and you spike it with all the internal standards, and not just one but all. So we spike them with the 17 dioxins, the 12 indicator PCBs, the 12 dioxin-like PCBs, the 6 indicator PCBs, and then we continue with the extraction if needed. If we have a sample of fat, oil, or whatever, we can directly spike the sample of oil, and go to the cleanup. So after the extraction, and I will discuss it, I will show you how we do that. We go to the cleanup. Before we go to the cleanup, we add another cleanup standard. And we use that for our control purposes. So if you have a poor result, then you can look in your internal standards, where did I make a mistake? And then we go to the GC high resolution mass spectrometer. And in between, you have to do all kinds of concentration, and Jeff already explained that that is time consuming and also a point of making errors. Okay. This is the method from the old days. We had a sock-slit extraction. It takes 24 hours overnight, use a lot of solvents, and then we went to our what we called semi-automated system. We started with gel permeation chromatography. It's over there. This is the GPC column with an HPLC system. Then we go to the alumina oxide, and then finally to the carbon. And in between, evaporation is necessary. Nowadays, if you have let's say, a sample of animal feed or a soil sample or a fish sample, we go to the PLE, the pressurized liquid extraction. And actually it's I explain it too, we have a lot of visitors, we have a lot of policy makers in our institute, and I explain to them, this kind of device, it's an expensive espresso machine. So here you put in your sample or your coffee, and your coffee is extracted with water, if you're lucky, and your animal feed is extracted with toluene, and you collect it over here, and then you can continue your analysis. It's a very elegant system. It takes you, let's say, between 15 and 30 minutes, and you use a very low amount of organic solvent. The next part is the power prep, and nowadays we have 9 modules, so we can run not 9 samples in every series, but we run 7 samples, because I would like to have in every series a procedure blank and a certified reference sample, or a sample which have been analyzed in the past, just for quality assurance. And we use this setup for the purification of the extract, of course. The first 2 columns, acidified silica and a mixed bed silica column, we use for getting rid of our fat. Then the second column, or actually the third column, is alumina. We use that for the removal of interfering compounds. And then the final column is the carbon column for separation, the non-ortho PCBs and the dioxins from the mono-ortho PCBs and the indicator PCBs. And also that fraction contains the PBDs, which we are routinely analyzing using GCMS in negative ion chemization. Okay. It has been explained by Jeff this morning already, but this is the scheme, and actually it's a brilliant system, and the brilliance is by simplicity. It's a number of, it's 2 6-way valves and a number of 2-way valves. And by switching them to one position, you can make a decision whether the solvent is going to the column or bypassing the column. It's very straightforward, and it takes you 24 steps to get your 2 fractions containing the compounds of interest. And the programming is very easy. And Jeff showed a whole paper of these things, but it's very, very, very convenient, very easy. Okay. Large volume reaction. I'm a big fan of large volume reaction. For the pesticides, we use large volume reaction just to get to improve our limits of detection. For the dioxins, we inject the same amount as in the past using the splitless injection, but the benefit of this system is within the evaporation. Nowadays, we do the automated evaporation after the sample cleanup. We use the power FEM from FMS, and it's automatically unattended concentrated down to half a milliliter, and then we directly inject from that half a milliliter 100 microliters onto the GC column. In the past we did the same, but after we went back to half a milliliter, we have to additional concentrate the sample down to 10 microliters, and then we inject 2 microliters. So we inject the same amount of matrix, but we inject only from a bigger starting volume. It saves a lot of time, and it improves really the recovery. Is it difficult? No. You have to work on it, of course, and troubleshooting is very important because sometimes you have a peak shape which is not very nicely, but then you have to adjust some of the parameters, and there are quite a lot of parameters which are important. Also, the liner is of importance. You need, of course, a deactivated liner. But it really helps to overcome an additional evaporation step. Okay, no, I can't see it on that screen, so I have to look at the main screen. The use of the PLE and the power prep resulted in a higher sample throughput. When I started to set up a facility at our institute, we were able to analyze 25 samples per week with a delivery time of approximately 2 weeks. Now we not to 10 samples. It's I think I made it last night quite late, but we increased the sample throughput from 25 to more than 100 samples a week. And whenever there's a crisis, we can increase that even more to 150, and we are fully prepared for that. So we have, whenever there's a crisis, we are going directly to work in 2 shifts. So we invested a lot of money in training all people to be able to help us in case of a crisis. Okay, shorter delivery time, 2 days, 3 days, better quality, and lower cost. Although we have to invest a lot of money, but we, with the same number of staff, we have increased the capacity with at least a factor of 4. Okay, now I come to some applications. The first one is the CPO problem. CPO is crude palm oil. And what we were confronted with was there was a company in the Netherlands. They imported palm oil from Asia, and it was controlled. It was checked in some laboratory, and they analyzed it, and they found that there was a very low amount of OCDD, approximately 200 picogram, resulting in a very, very low level on TEQ basis. Unfortunately, when it was shipped to Rotterdam, they processed the batch of crude palm oil in Rotterdam, and the processing is, they add some hydrogen and a catalyst, it's hardening. And the palm oil is used for human consumption, so they prepare all kinds of food from that, but they also use from the byproduct is for the feed industry. But both products are hardened, and by hardening it, the OCD was converted to lower chlorinated congeners with a higher TEF value. So initial value 200 picogram, and after it was hardened, after the process what was applied in Rotterdam, the final value was 1.5 picogram TEC per gram fat, and that was well above the EU maximum level. So there was a problem, and together with this company we have now a big project, and not only RIKILT is involved, but also some private laboratories like Nova Lab in Schiedam in the Netherlands and Eurofins are involved in that project, and we did some studies. And for instance, over here you can see, this is the initial crude palm oil, and it contained only 100 picograms. Is the red one is OCDD, and the green one are the non-2378 congeners, because we analyzed them as well. And after so the TEC level was well below the maximum EU level, but after this hardening process, and these are all steps in between, and all different parameters were applied, we see at the end there's hardly any OCDD. There's a small bit of 2378, but mainly hepta and hexas with a higher TEF value, so resulting in an exceeding of the maximum EU limit. Another example, even more strict, OCDF. We started with a sample containing 1500 picograms with a low TEQ level, and after hardening we ended up with 22 picogram TEQ per gram fat, so really a problem. Nowadays this company is capable of processing crude palm oil, hardening it with a high amount of OCDD, resulting in a very low level at the end. Okay, so they're making some improvements, and we will publish this work. Okay, the next one is the last 6 months in our laboratory. There was a colleague from Vietnam working, two. She is standing before the power prep machine with two of my colleagues, and she was working on two subjects. She did some analysis on eggs which were obtained in Vietnam, and she also, that was her main topic, she studied on the economic aspects of a method for analysis. I'll show you some results. Okay, this is during the Vietnam War. A lot of Agent Orange was used, and it was estimated that the pure TCDD was between 300 and 700 kilograms overall. And here you see, for instance, at the Bien Ho airport in Vietnam, the vessels containing the Agent Orange. Okay. So during the war, they sprayed the trees. First of all, to get rid of the leaves, so the Americans could see the Viet Cong people, and also to destroy the crops. But unfortunately, 4,000 people were killed, and still a lot of what you call bird defects are seen over there, and especially in the areas where the hotspots are. So it's really, that's terrible. Okay. My colleague too, she have, of course, she has all kinds of relatives living in around these hotspots, but also in some rural areas, and we asked all the relatives to send in to collect some eggs, boil them for 10 minutes, get off the yolk, and send it to our laboratory. And this is the area, and if there's anybody interested in the full report, please send me a message, and I will make sure that you get the report whenever it's finished, and it will be at the end of the month May, then it will be finished. Okay, so we did collect all the samples from these areas, and here you see the results. You will be shocked. What you see, for instance, here, the former bomb store, we have a TEQ level around 250 picograms TEQ on fat basis. The European level is 2.5, the maximum illegal level. So this is really, really, really high. And what you see is that the percentage of TCDD is quite high. So although it's 40, it's a long time ago, still the eggs are highly contaminated because the soil is contaminated. These are free-ranging chickens, of course, and the eggs are highly contaminated with dioxins, mainly 2378 TCD. But also the background areas, they are highly contaminated. They are higher than what is allowed in the European countries. And the people in Vietnam, they strongly believe that these free-range eggs are very good for the health of their children. So this report is, the first draft is now finished, and we sent it, of course, to the competent authorities, and we hope that they advise the people in these areas not to consume these eggs anymore. Okay. This is the analytical part. She also did some studies on what is the cost of an analysis? If I ask somebody here in the room, what is the cost of your analysis? And how is it built up? Nobody knows the exact answer, and that's why she always tries to, or she tried to make a model. So we have now a combination of Excel files with all the details, and it's based on administration, extraction, cleanup. For the calyx, of course, the cell culture, the measurement. These are the most important parameters. And she checked, for instance, the time needed for doing the fat extraction from fish, from eggs, and whatever. So I'm not going to show you the Excel files, but if you're interested, please give me a sign, and I'm very happy to show the Excel files to you. But the results are, okay, this is what you have to do. You have to fill in, of course, the lab capacity. Because everybody knows if you buy an expensive instrument from Thermo, a DFS, and you do only one sample in a yearly base per year, this sample will be very, very expensive. But you have to fill in the lab capacity, estimated average of number of samples, salary of the employees, and so on. This is the cost calculation in our laboratory, but we are a governmental laboratory, and this is for the Calyx. So what you see over here is the cost center for the administration, and it's about 50 euros. And so we spend a lot of time on writing down everything, and it has mainly to do with that we are accredited lab, ISO 17025. We spend a lot of time on writing down everything. Fat extraction, we do it now with the PLE, but for some we do it manually, and it's expensive. What you see in blue is the consumables, and what you see in red is the salary, and what you see in green is the, we call it indirect cost. My management doesn't like me to talk about overhead. It's really overhead. It's the cost of the management, of course, the building and so on. So we do it in this way. Okay, this is for the Calyx, and here you see it for the high resolution MS. And what you see over here is that the cleanup, the cost for the cleanups, it's mainly due to the cost for the equipment and the columns and the chemicals, and less to the labor and the overhead. Also for the high resolution mass spectrometer, it's mainly the cost of the instrument and less the cost for the labor and the overhead. If you combine these things, and that's what she has been working on, you can make a decision on basis of how many samples are you going to analyze and what is the percentage of positive or suspected samples you expect from the Calyx. And on basis of that, you can make a decision, am I going to invest my money on the Calyx or on the high resolution mass spectrometer? And together with Alex, we sent in not a kind of abstract, but we would like to present our results on MS technology on the bioassay, which will be held in Amsterdam, which is around the corner, in Amsterdam, end of May. And hopefully we can present there some alternative techniques for the bioassay. Okay. Final application, if I have some time. 10 minutes?
2-3 minutes.
Oh, sorry. Okay, that's okay. It's about HBCD and trisphenol A, and it was done by one of my colleagues, Guillaume Tendam. And these are the compounds, and we use for the, it's very short, we use for the cleanup, we use the power grip again, but we only use the silica column, the jumbo column, in combination with the SEPAC silica column. So we make an extract using the PLE. We dissolve the extract, or we concentrate the extract and put it on the power prep. And this is the method, very straightforward. We condition the columns with 200 milliliters of hexane, apply the sample, then wash the column, and then we elute the jumbo column with hexane dichloromethane, 50 to 50. And then we concentrate it down again, redissolve it in acetonitrile, and then we go to the LCMS. Here's some results. All kinds of samples we have been analyzing the last month. And one of the samples, and we are going to focus our study on that, is a sample of eggs, which is highly contaminated with HBCD. We don't know what the origin is of this egg sample, but we are working on that. It's really, it's really high. Okay. We have good recovery. We have we have nice accuracy with the Volker Helsa samples we analyzed. It's a very fast method. We can do 9 samples parallel. Of course, again, 7 real samples, 2 quality control samples, and it's not that too laborious. With that, I would like to thank you for your attention, and if you need any information, you can look for me on the on our internet website. Thank you.